Hello all, welcome to the course on operating systems. In this session, we are going to discuss about the memory view of a process, which is a topic of memory management. The objectives of this session include to explain the memory representation of a process, to introduce few terms related to memory management, to summarize various factors that influence process memory requirements. So let us begin. We all know that a process is the program under execution. That means whenever a program has to be executed, it has to be brought from the hard disk to the main memory. And whenever a process is stored in the main memory, it requires a certain amount of memory for storing various types of information, which include text segment, data segment, heap segment, and stack segment. First of all, the text segment, which is also known as the code segment, which is also called as a text segment, which stores the executable instructions. The next one is data segment, which includes both initialized data as well as uninitialized data. Initialized data includes the global variables and static variables that are initialized by the programmer in the program. On the other hand, uninitialized data includes the variables that are not explicitly initialized by the programmer, but they will be used in the program. Next comes the stack segment. We all know that whenever a function is called in a program, the context of the caller function has to be stored in the stack, so that after executing the call program, whenever the control comes back to the caller program, it has to be retained. So for that purpose, we need a stack memory. And there is one more segment which is called as the heap segment, and this segment of memory is used for dynamic memory allocation. And if you look at the diagram, the heap memory keeps on increasing towards the stack depending on the requirement. That is, whenever there is a requirement for dynamic memory allocation, the heap keeps on growing towards the stack memory. And similarly, the stack memory, depending on the number of function calls involved in the program, the stack memory keeps on increasing from this pointer towards the heap. So when the stack pointer meets the heap pointer, that means this is the available space for the process in the memory. And if the heap keeps on growing towards the stack and stack keeps on growing towards the heap, there is a point when both of these pointers meet, and in that case we say that the memory for the process is exhausted. That means there is no available memory for the process. Now let us discuss about few more terms that are related to the memory representation of a process. In addition to the text segment, data segment, heap segment, and stack segment, process also requires memory for various reasons, which include context switching. That means whenever the CPU switches between different processes, it must save and restore the process registers, program counter, and memory mapping. That means whenever there is a context switch from one process to another process, the CPU has to save the current context of the process before switching to the new process. So that is illustrated in this diagram. So in this case, there are two processes, P1 and P2. Initially, the CPU is executing the process P1. And whenever there is an interrupt, in such a case, the CPU has to save the status into the process control block. That means the state of P1 has to be stored in PCB1 before the CPU switches to another process P2. And then P2 continues to execute. And again, whenever there is an interrupt, in that case, the state of process P2 has to be stored in PCB2. And then it has to reload the state of PCB1. Only then it can switch to process P1 for execution. So whenever there is such type of context switching, it requires additional memory space in the main memory. And next term is the virtual memory. Virtual memory is a memory management technique in which the secondary memory can be used as part of the main memory. We all know that the process have to be stored in the main memory whenever they are in execution. And at any given point of time, there are multiple processes that are currently running. So in such a case, the available RAM of the computer may not be sufficient to accommodate all the processes which are currently running. In such a case, the operating system uses the secondary storage as a backing store so that the entire disk space is available as the main memory. Though the main memory is not having that much capacity, there is a mechanism of using the entire disk space as the main memory. So such concept is called as a virtual memory concept. So it is a memory management technique in which secondary memory can be used as part of the main memory. We all know that the process can be in different states, starting from the ready state, running state, termination state, waiting state. So whenever a process is in the waiting state, then it can be brought to the hard disk. And only the processes that are currently running can be given space in the main memory. Virtual memory allows process to have the illusion of having their own dedicated memory space, even though they share physical RAM with other processes. That means whenever a process is currently executed by the CPU, only those processes will be given the space in the main memory. On the other hand, whatever a process, if it is in the ready state or in the waiting state, it can be swapped out to the hard disk space. So whenever it comes into the running state again, only in such a case, the process can be brought back to the main memory. So this process of swapping out and swapping in the process between the main memory and the hard disk are termed as swap out and swap in. The next term is page fault. That means if a process tries to access a virtual memory address that is not currently in physical memory. That means we are bringing some of the instructions to the hard disk, and if a process tries to access a memory location or an instruction which is not present in the main memory but it is present in the hard disk. In such a case, we say that there is a page fault. So whenever a page fault occurs, the operating system is responsible for bringing the required page from the secondary storage into the physical memory. Here physical memory is nothing but the main memory. So whenever the instruction is not present in the main memory, the operating system has to bring the instructions which are stored in the backing store or the hard disk into the main memory. So this is the case when a page fault occurs. So if the instructions are not present in the main memory, we say that it is a page fault. And whenever there is a page fault, the operating system has to bring the instructions back from the hard disk to the main memory for execution. Next one is address translation. Just now we have seen that the entire hard disk space is being used as the main memory. So there should be a mechanism that is required in order to map the addresses of the physical memory or the main memory to the actual addresses of the hard disk. So under virtual memory, the process virtual address must be translated to the physical memory address by the operating system's memory management unit. So it is the responsibility of the memory management unit in order to map the main memory addresses to the actual disk space addresses. Next term is address space. Each process in an operating system is allocated its own virtual address space. Operating system maintains a page table that stores the mapping between the virtual addresses used by the process and the corresponding physical addresses. That means always the process need not be in the main memory. Whenever it is in the ready state or in the waiting state, it can be brought to the virtual address space. So for each process, a page table has to be maintained in order to store what are the corresponding virtual addresses corresponding to the physical address. So such type of storage is called as the page table. So coming to the summary of process memory usage requirements, we already have seen that there are 4 different segments. One is a text segment, which is for the code, for storing the code and instructions. So the program executable instructions are basically stored in this segment. And the next segment is to store data and variables, which includes both global and static variables. And it again, in turn, is divided into 2 subsegments, which are initialized data and uninitialized data. Next one is heap segment, which is used for dynamic memory allocation. If at all the program instructions include methods or functions called as malloc or calloc, in such a case, dynamic memory has to be allotted. So for accommodating the dynamically required memory for a process, the heap segment is being used. And the next one is stack segment or stack space, which is required whenever a program includes function calls. So in order to save the current context of the caller program before the program controller switches to the called function. So once the called function is executed, then again the control comes back to the caller function and it retrieves the context of the function by using this stack. In addition to these 4 segments, memory is also required for a process whenever there are certain data interactions with the external resources, and also whenever some data caching mechanisms are implemented. For example, if we look at the memory hierarchy, on top we have the cache memory, and below that we have the main memory space, and then we have the disk storage at the bottom. So as we move from top to bottom, the speed decreases, whereas the memory capacity increases. So in order to improve the performance of the computer, the data has to be, the data and instructions have to be brought from the hard disk to the main memory, and also the frequently used instructions can be stored in the cache memory. In that case, there should be the data swapping between the cache memory and the main memory. So in order to improve the performance of the computer, the data caching techniques are used, and for implementing the data caching techniques, each process may require some additional space. Next one is multi-threading and concurrency. For example, in the inter-process communication, one process communicates with the other process by using various techniques, including shared memory. So whenever 2 processes have to be executed concurrently, they can do so by using the shared memory. So in that case, the process that initiates the communication creates the shared memory, and the process that is using this shared memory can be able to interact with the process. So if at all multi-threading or concurrency control are implemented, a process also requires an additional space which can be used as a shared memory. In addition to this, if at all the program is using some third-party libraries, memory is also required for storing the functions of these third-party libraries. So the summary is the memory requirements of a process can change during the execution of the process, depending upon the data caching techniques that are being implemented or the multi-threading concepts that are being implemented or the usage of the third-party libraries. So with this, we came to the end of the memory usage requirements of a process, which is part of the memory view of a process. Thank you.